Hello everybody, welcome to the course of the Basic Coordination Chemistry. I am Shubhendu Naskor from team 16U1_010 of FDP201X. Herein I am going to present the first topic of the course, Introduction to Coordination Chemistry. At first, we must know some definition. What is coordination chemistry? That is when a metal combines with the neutral molecule or ions which are known as ligands via coordinate bonds to give a new entity that is called a coordination complex, and the related chemistry is known as coordination chemistry. In this coordination complex, the ligands are arranged around the metal in the first sphere of attraction in preferred geometries. Coordination number, the number of the ligands bound around the metal ion is called the coordination number, and the coordination sphere that is created by the array of the ligands around the central metal. At this point, we should have a clear idea about the double salt and the complex salt and the differences. When a double salt is dissolved in a solvent, that gives the taste of the corresponding cations and anions, but when a complex salt is dissolved in solvent, that does not respond to the taste of the metal ion because it produces a complex ion. Here we consider the complexation process. It is a donor-acceptor interaction where the metal behaves as an acceptor and the ligands behave as a donor, and the ligands and their classifications. In coordination chemistry, ligands are molecules or ions which donate one or more pairs of electrons to the central metal atoms or ions to form the coordinate bond. These ligands may be classified according to the number of the coordination positions they occupy. If they occupy only one position, then it is a monodentate. If two, then it is a bidentate. If three, then it is tridentate, and so on. So on the basis of denticity, they have been classified in this way. Monodentate, they have only one lone pair of electron. Bidentate, they have two lone pair of electrons. Tridentate, 3, etc. In this way, hexadentate is represented by ethylene diamine tetraacetate anion. So the number of the donor atoms is sometimes called the denticity of the ligand. A ligand which shows different denticity is called a flexidentate ligand. Thus, EDTA, though is a hexadentate ligand, sometimes it may function as a pentadentate or tetradentate ligand. Chelates. It comes from the Greek word chela, which means crab's claw, and similarly, when a ligand is bound to the metal, it forms some rings, and that ring is known as the chelate ring. Now, chelating ligands having the anionic donor site may simultaneously satisfy both the secondary and the primary valency. So about the secondary and primary valency, we are going to discuss this in the next few slides in Werner's coordination theory. Now, there is another type of ligand known as Brazil ligand, which contains more than one lone pair of electron and which simultaneously donate more than one lone pair of electron to more number of metal ions. This is the Werner's coordination theory, for which he got the Nobel Prize in 1913. He studied on some complexes and then characterized them and measured their physical properties. Here he obtained he measured the conductance value, and it shows that for these molecules, as we move from top to bottom, the conductance decreases in this way. So, and when it is reacted with silver nitrate, the number of moles of per mole of the complex, the number of moles of silver chloride precipitate is also decreases in this way. So on this basis, he proposed the total number of ions present in the species is like that. Herein, he proposed two types of valency, primary and secondary valency. Primary valency is the formal oxidation state of the metal ion, whereas the secondary valency is the total number of the ligand atoms attached to the central metal ion. Werner proposed putting all ligands, those satisfy the secondary valency, should be placed within the sphere of the third brackets, and the free ions or cations that dissociate when they dissolve in water outside the brackets. The molecular formula of PTCl4 can be written is this way. In another experiment, he performed the same same activities on the cobalt system, and he obtained these results. It shows that with 6 ammonia, 5 ammonia, and these 4 ammonia, different colored complex were produced, and afterwards he proposed the molecular formula in this way. Herein we would like to have a look at these last two molecules. They are basically isomer having same molecular formula. One is green, another is violet, and here he proposed the dissociation of all the molecules in this way, where this cobalt NH3 whole 6 ClC, they produces 3 chloride, this one produces 2 chloride, and this one produces 1 chloride. And for this molecule, the two forms are obtained, red and green, and they are, one is in the cis form where 2 chloride ions are on the same side of the cobalt metal, whereas in trans form they are on the opposite side. Now, what is coordination number and their corresponding stereochemistry? The most significant part of the coordination Varna's theory lies in the postulates of the directional nature of the metal ligand bond. There are a number of physical methods now available, for which of which X-ray crystallography is the most important, which can locate the actual position of the atoms in the crystal. So in this section we shall get familiarity with the common geometries found in the coordination compounds. So since the attraction between the metal ion and the dipolar molecules or anions is involved, the coordination number will tend to be as large as possible. Now, the arrangement in an Ml2 type of complex, it should be linear, such a geometry to maximize the ligand-ligand distance and hence to minimize the repulsion between the two ligand groups. Similarly, Ml3 will adopt a triangular geometry, and Ml4 may adopt a tetrahedral or square planar. Ml5 will adopt a trigonal bipyramid or square pyramidal geometry. So here is the table which shows the list of examples and coordination number and the corresponding stereochemistry with examples. Okay, for 2 AgNH3 whole 2 plus or mercury Ag plus Ag2 cyanide 2 copper chloride, basically cupric chloride, they are linear in nature. For coordination number 3, they are trigonal planar. For 4, tetrahedral square planar. For 5, TBP. For 5, it also shows square pyramidal, and for 6, it is octahedral. So thank you very much for listening. Hope this may work for you. Thank you very much.